Okay, so in this video we are going to solve another rigid body kinematics problem, and the picture of the system is given here. I took the picture from the textbook where this example appears, and it's a little bit it's a little bit involved system in terms of its 3D orientations, and so I decided to, instead of drawing a freehand picture, to take the diagram from the textbook itself. So essentially there is a cylindrical tube, as you can see here. It is a bit distorted because of the picture that I took, but it's a cylindrical tube. That cylindrical tube has a certain radius that we can find out, but let us say this is a cylindrical tube, and in the middle of the tube there is this pipe which is rotating with an angular velocity of angular velocity of capital omega, and this portion of the tube is bent from the central vertical piece. It is bent, and it is bent at an angle of beta. So this piece which is bent is of length L, and at the end of this bent piece there is a disc of radius capital R. The center of the disc is given by the point A. The angle beta is of course fixed. Now if we take a projection of this over here, then we see that this part going from B to A is the bent part of the rod. So B is essentially this point over here. So you can say B is the point shown here, and so from B to A, over the distance L, there is this bent part. Now here is the disc. It is of radius R. It is a circular disc. Again, it is a bit distorted just because of the way I took the picture. Now the interesting thing is that this disc, or rather as this rod turns with an angular velocity of capital omega, the disc maintains a single point contact on the inner inner surface of the cylinder. So there is always a point of contact C between the disc and the inner surface of the cylinder, and so the disc essentially rolls without slipping on this inner surface of the cylinder as the rod rotates with an angular velocity capital omega. And so the question in this, there are several ways of looking at this problem and several types of things that we can solve for, but we will start off with finding two different quantities, and that is the angular velocity of this disc, the absolute angular velocity of this disc, and the angular acceleration of this disc. So find the angular velocity of the disc. That's number one, and number two is find the angular acceleration of the disc. So these are the two quantities. So it is interesting, first of all, before we start solving the problem, to note that while the rod, which is going through the center of the cylindrical tumbler, is turning with a constant angular velocity, the problem indicates that the disc itself can have an angular acceleration. Note that the rod does not have any angular acceleration because it is just rotating with an constant angular speed. But because of this constraint, the rolling constraint, the problem basically indicates that the disc itself has got an angular acceleration, and that is what we are going to solve for. Now let us also give an overview of the coordinate system that we are going to be using to indicate all the unit vectors and so on. So this is probably a little bit difficult to see from this picture, but I'm going to sketch a little bit more clearer picture in a second. Essentially, this direction from B to A is named as the Z direction. This is per the problem in the book, and X is mutually perpendicular to it. So you can think of X kind of being let's say in the direction from A to C, where C is that point of contact. Okay, so X is in the direction from A to C. So for the sake of clarity, I'm going to draw this schematic again. So we have this scenario where you have A here, B here, C is this point. This dashed surface represents the vertical surface of the inner surface, the inner vertical surface of the cylinder, and this direction is the z-axis and this direction is the x-axis. So you can see that the y-axis is then this way, forming a right-handed coordinate system. Now this bar is turning with an angular velocity capital omega, and as it turns and the disk rolls without slipping, the disk has an angular velocity phi dot. Okay, and this distance is r. That's the radius of the disk. Okay, and by the way, this vertical, which is the fixed vertical direction, let's call that capital Z. All right, so that's the capital Z, that's the inertial z-axis. Now we also, before we start solving, we also need to understand or get a proper idea of the rotating XYZ axis. So let's clarify that. So the rotating XYZ axis actually is an axis which has an origin at B, and its z-axis is always along the bent part of the rod, right? So z-axis is always along the bent part of the rod. The x-axis is always directed from A towards C. Okay, so the x-axis is kind of always radial, but not really radial in the horizontal direction, but radial at an inclined angle, but nevertheless it is radial. And since this angle is beta, so you can see that the x-axis makes an angle beta with the horizontal, right? So the x-axis is radial, but not really along the radius, but making an angle. Now it is important to note that the XYZ axis is fixed to BA, but it is not fixed to the disk. So XYZ rotating axis is fixed to the bent part of rod, and it is not fixed to the disk. Okay, so how do we deduce that? How do we deduce from this definition that xyz is, the small xyz that is not fixed to the disk? Well, if small xyz was fixed to the disk, then you would have to show, so the small xyz is not fixed to the disk, and the reason we can say that it is not fixed to the disk is because if it was fixed to the disk, then we would have to work with the most generalized or the most general configuration of that body fixed XYZ, and that most general body fixed XYZ would not have this orientation. Rather, the orientation would have to be X as usual or Z as usual, but X would have to have a general configuration of making an angle phi, and similarly Y would also have to be shown correspondingly. So if XYZ was fixed to the disk, then we would have to designate, actually this would not be phi, phi would be from a certain fixed point. So if XYZ was fixed to the disk, then X would have to be such that the general configuration makes an angle phi, okay, with respect to a fixed direction. That would make the XYZ configuration the most general configuration, okay. And so we cannot treat the XYZ as shown in this diagram or in this diagram as an XYZ that is fixed to the disk. We have to treat it as an XYZ that is fixed to this bent part of the rod, okay. So we'll keep that in mind, and I'm going to erase these notes that I have made here just so that it does not confuse us, and we can revisit this later on once we have solved the problem. Alright, so with this understanding, we'll start the problem. We'll indicate the absolute angular velocity of the disk as omega d. So omega d, as we can see, has got two different components. One is the fact that the vertical part of the rod is turning with an angular velocity of capital omega in the in the negative z direction. So this is the negative capital Z, positive capital Z direction, and capital omega is in the other way. So you have negative capital omega, capital K. So this capital K represents the unit vector along the capital Z direction, that is the inertial Z direction. Furthermore, the disk itself, because of its spinning, has got an angular velocity of phi dot, and that is in the negative small z direction. So you have negative phi dot small k, where small k is the unit vector along the rotating z-axis. So this is our rotating xyz axis, and small k is the unit vector along this z-axis. Capital K is the unit vector along this z-axis. Okay, so while this is the formulation of the angular velocity, question is that what is phi dot? So we do not know what phi dot is, but as you can see intuitively, if this disk rolls without slipping on the inner surface of the cylinder, then this angular velocity capital omega will automatically determine phi dot. So phi dot will be determined by this capital omega and other geometric conditions. So that is what we are going to determine, and for that we are going to use the rigid body kinematics. So the way we are going to proceed, first of all, is that we are going to resolve this this capital omega along the rotating frame. So we have negative, you can see omega is in this direction, so capital omega cosine beta is in the negative small z direction. So and capital omega sine beta is in the positive x, small x direction. Right, so the small x direction is being indicated by the unit vector I. So while this is good, we still have to determine phi dot. So the way we determine phi dot is by imposing the fact that the point C is has a zero velocity, because the cylinder is fixed and the disk is rolling without slipping. So therefore at the point of contact, which is the point C, the velocity of C has to be equal to 0. Now we can, the way we impose this and find the angular velocity is the following. We say that Vc is equal to Va plus omega disk cross rho c with respect to A. Right? This is the basic equation that relates the velocity of 2 points on the same rigid body. So if 2 points are on the same rigid body, then they are related by this equation. This is a simplification of the 3-term velocity equation in a rotating frame. It does not have the relative velocity component, the relative velocity in rotating frame. That component is not there, and this is because both A and C are assumed to be part of the same rigid body. Okay, so we'll start with this. So so we'll make a note that C and A are part of the same rigid body, and in this case the disk. All right, so now let us see what is what are the individual components. Now let us consider Vc. Now Vc is equal to 0 because C is the point of contact, and it is rolling without, and the disk is rolling without slipping. Now consider Va. Va, if we consult this picture here, as the bent part rotates with an angular velocity of capital omega about this vertical axis, then the point A is going to have a velocity into the surface of this page, and so therefore the point A is going to have a velocity in the negative y direction, and furthermore that velocity is going to be given by, if we extend this vertical line, it's going to be given by the angular velocity times the perpendicular distance from A from this vertical axis, because A is just going in a circle. A is just forming a circle here, right? So this distance is L sine beta, right? So L sine beta times omega is the velocity with which the point A is moving. So L sine beta times capital omega, and you can see that the point A, by virtue of the direction that has been attributed to omega, capital Omega, the point A is going inwards into the page, whereas small y is pointing outwards, so it is negative, and the unit vector is going to be j. Alright. Also, we note that rho c with respect to A is going to be this vector. So rho c with respect to A is this vector, and this vector has a length of r, and it is going to be in the direction of I. So it is r I. And note that this is one place where we are actually making use of the definition of the rotating frame. The rotating frame here is not fixed to the disk, it is fixed to the bent part, and because of that, even though the point of contact C changes, that is, the disk has different points of contact with the cylinder at different times, but nevertheless x direction is always going to be in the direction of A to C, and so this is true at all times. Now let us incorporate these vectors into our main velocity equation. So we have 0 is equal to negative L sine beta times capital Omega times j plus the angular velocity of the disk, which is negative omega cosine beta minus phi dot k plus omega sine beta I, this cross Ri. Right, so we can see that once we do this cross product, I cross I is going to be 0, so the only thing that will be non-zero is the k cross I, and k cross I gives us j, because our right-handed coordinate system is I, j, k, with the cross products taking place in this manner. So k cross I is going to give us positive j. So therefore we have negative L sine beta capital Omega minus r times omega cosine beta plus phi dot j. So now because of the left hand side being 0, we can say that therefore r times omega cosine beta plus phi dot plus L sine beta capital Omega is equal to 0. So from here we see that omega or phi dot is equal to negative omega times L sine beta plus r cosine beta divided by capital R. Which gives us phi dot to be equal to minus omega times L over R sine beta plus cosine beta. So that's the angular velocity. That's the angular velocity phi dot. Now this is not it, because we are seeking to find the net angular velocity of the disk, which is omega d. So therefore omega d is equal to minus omega cosine beta So let's consider this expression, and we are going to substitute for phi dot. So minus phi dot is going to be plus omega L over R sine beta plus cosine beta whole thing times k. Let me just plus omega sine beta times I. And there is going to be this cancellation, because omega cosine beta here is going to cancel this negative omega cosine beta, and we would be left with omega d, which is the net angular velocity of the disk, to be equal to capital Omega L over R sine beta k plus capital Omega sine beta I. Okay, or in other words, omega d is equal to capital Omega sine beta times L over R k plus I. Okay, so we have solved the first part of the problem, and we have found the angular velocity of the disk. Now the second part of the problem asks for the angular acceleration of the disk. So going back, we are looking to find the angular acceleration of this disk, and if you take a look at this expression for the angular velocity, it seems like it is constant because all the entries over here are constant. Beta is a constant, L and R are constants, capital Omega is a constant. So it looks like it's a constant, but it is not clearly, because here k and I represent the unit vectors in the small z and small x direction respectively, and clearly that's a rotating coordinate frame. And so therefore when we find the angular acceleration, what we need to do is we need to consider the angular velocities of this of these unit vectors. So I am, in the interest of time, I am going to defer that to the next video, where what we will do is we will start over here with this angular velocity expression, and we'll take the time derivative. So we'll find the angular acceleration through direct differentiation. We'll take the time derivative of this with the consideration that k and I are rotating unit vectors, and the angular velocity of the rotating unit vectors k and I and j will have to be considered. There is a subtlety there that we need to clarify as we take the time derivatives. So our approach in finding the angular acceleration is going to be AD, that is the angular acceleration of the disk, is going to be capital Omega sine beta divided or times L over R k dot plus I dot, and k dot is going to be omega cross k, and I dot is going to be omega cross I, and here omega is going to be the angular velocity of the xyz, that is ijk, the small ijk triad. and that angular velocity, if you think, is not same as the angular velocity of the disk, because the triad is not fixed to the disk, it is fixed to the inclined part of the bent part of this rod, BA. So that is something that we will have to consider carefully in order to get the angular acceleration of the disk, which we will pursue in the following video. Thank you so much.